morning is Alexis Prévost from Geneva. He will give the first lecture of his lecture class.
All right. Thank you very much. And thank you for the opportunity to give this mini course here. So this mini course will be about mainly random interlacements and especially local uniqueness properties of random interlacements, and also application to the study of the Gaussian phi field via so-called isomorphism theorems. But okay, before going into any of that, I want to give like a proper introduction to random interlacements. And explain a bit, rather than just giving the definition, the motivation behind it and where it comes from. So it's a model which was introduced by Snitman in 2010. And in a sense, you can see this as a model for a random walk starting at infinity on a transient graph. So, okay, the question is, what does it mean to start a random walk from infinity? So before seeing that on an infinite graph like ZD, on which I will focus for the rest of the course, I will rather look at finite graphs first to try to understand what it means. Okay, so let's say G is now a finite graph. And let's say that some points are part of the boundary of the graph that you can choose. And I call this boundary, I don't know, you say that in English, des ronds, partial. Okay, so you have your graph, okay? And then some vertices are part of the boundary, and these vertices I will merge them together into a single boundary point, like that. Okay, and I will replace all of my edge that were going to a boundary point by now an edge going to my boundary point here. Okay. So you imagine what I want to do at the end of the day is take G to be a big ball and let this ball go to infinity to my infinite graph, right? At the end of the day, and the boundary will just be the boundary of my ball. That will be the goal. So now let's say I start a random walk. So I want to start from infinity, right? So infinity on this finite graph, you can see it as this is the boundary of my graph. Okay, and I start here, so. And then, well, I just do a simple random walk, so this means that I choose any of the edge at random, uniformly. Right, so let's say I choose this one. And then once I'm here, I just follow the usual random walk on my graph. So I have some excursions here inside my graph. And at some point, I might come back here to a point which is near the boundary, and maybe I come back then to my boundary point, like that, okay? With probability uniform among the number of edges which are adjacent to this vertex here. And then I keep going, I'm just a random walk, right? On this graph, the boundary in the sense plays no particular role except that I start from there. And I just have a second excursion inside of my graph of my walk, and so on and so forth. Okay, and I keep running my walk like that. So, one thing to take into account for this kind of graph is what does time reversal look like. So for this, let me first call dx the degree of a vertex x in my graph. And like the definition, right, of my walk is that I jump from x to y with probability 1 over dx for any neighbor of x. Okay, so it's just uniformly at 1 among the possible jumps. And then time reversal. So the question is, how can I compare the probability that my random walk goes forward as it was doing in this direction, right, and then coming back to the reverse path, that is I start from here and I follow this path instead. Okay? And so if you just look at a simple event, let's say you start in x, and then you go to x1 and so on, you end up in xn. This, so first to go from x to x1, it will cost 1 over dx, and then you have the product, so for I between 1 and n minus 1 of 1 over dxi. Okay, and this product, I can do a time reversal. So here this dx cancel, because I put it here in the beginning, and this product I can just do a time reversal, that is I change my index here I by n minus I, and this just becomes the product of the 1 over dx n minus I, right? And then if I want, I can also add again the last vertex now. So I add maybe first 1 over dxn times dxn. And what do I see here? This is exactly the properties that my work start in xn, then jump to xn minus 1 and so on. Right, so this is dxn pxn at x1 equals xn minus 1, and so on until you come back in x. Okay, so I've been able to term reverse my work. There is, however, a price to pay. I need here to multiply by the degree of the starting point on both sides. And I can do that for any path, and so in general, I can always reverse any event as long as I pay the correct factors in front. All right, so now I want to understand this picture here. And more precisely, what I want to do is I want to understand what is happening locally. So let's say I fix a given set k, okay, which is just fixed. And you imagine that in the end, I will make my boundary goes to infinity, and my set k will be fixed, okay? And the question is, how does my random walk look like locally? So that is, how does it look like when I restrict it to just the excursion that it's k, okay? So this random walk, the question is, okay, I have a certain number of excursions. The number of excursions will depend on the time, right, that your random walk have been running. We will come back to that later. But at the moment, the question is, what is the probability that an excursion hits my set k? Okay? So if you, let's say you fix an excursion, maybe the first one or something like that, right, inside your graph. So that means outside your boundary point, right? What is the probability that one excursion hits the set k in some point x, which is some point on the boundary of k, where it's possible that I hit on this point. So this, I can just write it as this is, I have a random walk, and I want that this random walk hit k in x, and that it hit k before coming back to my boundary point, otherwise I wouldn't need to start a new excursion. So just some notation here. hk, this is the hitting time of a set, whereas h tilde k, this is the first return time to my set. So I don't count time 0. Okay. And now what I can do is use my time reversal properties that I just proved and look, okay, if I start from here and I end up here in x, okay, then this is the same as saying time reversal, I start in x, and then this path here never hit k, right, and it ends up on my boundary point. So this is the same as the probability starting in x that I hit my boundary point, I mean that I hit it, that's it. And I hit it before coming back to k. And of course, I need to pay my degree factor over there. So this is, so I need to multiply by dx and 1 over the boundary.
So in the first probability, you need to have starting point as a boundary or not? At the first,
Here, you mean?
the left.
Yeah, this is a starting. This is for my work starting at the boundary. So that any of the excursion, what I call an excursion, is any part of the work that starts at the boundary, and I split into excursion. And so what I see here, this is what is called the equilibrium measure of my set K. Okay. So, well, this is my definition. This is the equilibrium measure of the set K. I add here the G to say this is for my graph that I'm looking at here. Because sometimes when I take the limit, this will be important. And this is just what appears. Okay? This is just a definition. And so, in particular, the probability that one excursion hits the set K anywhere, this is just the sum over x of the previous. So this is 1 over the degree of the boundary times the sum of my equilibrium measure. And this sum of the equilibrium measure, this is the capacity. This is the definition. Okay. If you know a bit about random interlacement, I've seen a few talks about it, you see that the capacity of the set is a central object, and this is where it comes from. It appears naturally when you do your time reversal property. Okay. So now I understand one excursion. Okay. How does it hit K? So and then once I understand where it hits K, the rest of the law of this excursion is clear, because then forward I'm just like a random walk until I come back in the boundary, and backward I'm also a random walk until I come back to the boundary, but just I never visit K when I go backward here. Okay, so I understand completely the law of this excursion. The question is, how many excursions do I have? So I will do here a small time change, because the problem is that in this picture, if you just let time for your random walk run freely, then you might have like excursions that are a bit weird, which is the last excursion, which will do something like that, and then that will stop at the final time of your walk. And this excursion is a bit weird compared to the other because it's not a full excursion, it stops somewhere in the middle. So I want to avoid this kind of picture so that all the excursion looks the same and have the same law. So I will just always keep running until I come back to my boundary point. So in order to do that, let me define the local time of a vertex. So this is the total time spent at this vertex. But this is for the continuous random walk. And I will explain later why I use the continuous time random walk. It's actually not completely necessary. But it will make my analysis a bit easier. So what this means is that I count how many times I come back in X, and every time I come back in X, I wait an exponential time. Okay, so this is an exponential random variable. They are IID, okay, both in X and in K every time I come back, and also in space. And the parameter is dx. Okay, why is the parameter dx? This is just correspond to say I wait time which is exponential 1 to jump to any edge which is nearby. So in total, how long do I wait in x? I wait an exponential time with parameter dx, right? It's the minimum of all the exponential 1, of the dx exponential 1 variable. So this is the natural parameterization for the continuous time random walk. And with this definition, now I will run my random walk until a given time, which is this tu time, which is the first time that the walk has spent the time u at the boundary. Okay, and the advantage of waiting until this time is that I know that at this time tu, and this is the first time that my local time at the boundary reach u, so I know I am at the boundary. Okay, so I know I really, at this time tu, I really finished all my excursion and they really all came back to the boundary. So this is my new time parameterization. If you want, u plays the role of your time, or it plays the role of how many excursions do I have. Okay?
So it's L and partial equal 1 or u?
U.
Okay. That's, u is an integer.
Yeah, no, u is any positive number. Since I have exponential variable, it can take. Okay, so this is my new time parameterization. Now the question is, at this time, tu, how many excursions do I have? Okay, so at time tu, there are Poisson number of excursions. for my walk. Why? It is just what you're wondering when. So my local time at u, at the boundary point, this is just a sum of exponential random variable, and you're wondering when is your sum of exponential random variable equal to u, okay? And this is a Poisson random variable. When does the first time that like this is usual Poisson process thing. That the first time a sum of exponential random variable reaches a point is a Poisson random variable, and the parameter is u times the parameter of your exponential. Yeah.
Greater than or equal to u?
I mean, we can, yeah. But it will reach u at some point. I mean,
Okay.
it's continuous, so it's equivalent. I mean, okay, it depends. Yeah, sure. Okay, if you see it as I wrote it here, you're right. I need to do that. Yeah. Thank you. If you see it from the point of view of a continuous time random walk, then you don't. But yeah. Okay, so I have a Poisson number of trajectory of excursions, and each of my excursions, I know what is the probability that it is k in x. So I want to understand the restriction of all my excursions to k. Okay, so this means that there are. So this is the thinning property of Poisson random variable. U capacity of k trajectories eating k, or maybe excursion. Okay, this is a thinning property because the probability to eat k is 1 over this degree of the boundary times the capacity. Okay, so this is exactly what happens for random interlacement. Okay, for interlacement, you have a Poisson number of trajectory which eat a set k. And so more precisely, maybe let me now be a bit more precise on, okay, now I've understood what is the law of like how many eat k. Now the question is what is the total law of the process if I restrict it to the trajectories that eat k. Okay. So the walk at time tu restricted to excursions eating k. This is now a Poisson point process. With intensity u times the equilibrium times the measure that we call nu k. Maybe let me keep the dependency also on. Okay, and this nu, what is it? It is exactly the law of my trajectories. So I can write it explicitly. With nu k of some event. So this is a measure on your trajectories at eat k. Okay, and you take a Poisson point process with this intensity. And so you have the sum over k of the equilibrium measure of x. So this is telling you what is your starting point, and you know that you start in x with probability which is proportional to the equilibrium measure. This is what we proved above. And then you have your backward part. So the backward part of your walk. So once you know you start in x, what was before x, this is just a random walk, but that is but that never eats k. So maybe I should say, and it's a random walk which is stopped on eating the boundaries because I just do one excursion. So for backward, I have a random walk which never come back in k. Just by time reversal, I just use again the time reversal property which tells me that starting from the boundary and eating k in x is the same as starting from x and coming back in the boundary without eating k. This is exactly what I wrote here. And then forward, I am just a random walk. once I have xk for the first time, I just behave like a round.
Sorry, what is that word next to you?
What is what?
The word next to TU, the walk at time TU.
Restricted to excursion. Restricted.
Oh, restricted.
Yeah. And so, this is the random interlacement process. On G. And so the random interlacement process on G, what is it? It is a process that for each k, when I restrict it to k, I have a Poisson point process with this intensity, okay, which is defined. All right, and maybe add at a value. You with your time. Okay, so on this finite graph, my random interlacement is just a walk starting from the boundary and run for a certain number of excursions that depends on you. Well, you is your time, which is given by that. Okay. Well, what do you do now if you want to know what happens on infinite graph? You do the same. You take a Poisson point process with this intensity. Okay, this intensity is not well defined because you don't have a boundary point anymore. But let's say that G is an infinite and even transient graph. Then I can still define this intensity measure. I just need to replace my boundary by infinity. I think the boundary is replaced by running for an infinite time. And the only difference is I also need to change my definition of my equilibrium measure here, but I mean I can also do that. No. So okay, I guess here's let me maybe write it here. The equilibrium measure will be defined as just a probability that I never come back in K. Okay, and if I take a sequence of, if I take G, a sequence of balls that grow to my infinite graph, okay, then this intensity measure on my finite graph, which is my ball, okay, will converge to my intensity measure on my infinite graph. Okay, so this walk started here from the boundary of the ball of size n converges in the limit to a Poisson point process with this intensity measure when I restrict it to k. Okay, so now let's define random interlacement properly. Yeah.
I'm a bit confused. When you write the walk at time tu, shouldn't be the walk before time tu? I mean.
Yeah, I mean up to.
Up to. And you start your walk where? On the boundary?
On the boundary.
On the boundary.
Yeah.
Okay, thank you.
And this is a theorem, which shows a theorem due to Smithman. I mean, didn't exactly prove it like that, but essentially proved it like that. The construction that I presented here is also due to Smithman, but later, more in 2012, which says that there exists a measure nu G, whose restriction to trajectories it in K is exactly my measure nu gk from above for any k fine. And the proof is clear at this point, should be, hopefully. This is just why? Because if I take k included in k prime, then the restriction of my intensity nu jk prime to excursion or trajectory it in k is just nu gk. Why is that? Well, on a finite graph, I know this is true because my restriction to, let's say I have another set here, k prime. Okay, I know that my restriction, my new gk prime, this is my intensity measure of my walk restricted to k prime, and new gk is the intensity measure of the walk restricted to k, right? So if I first restrict to k prime and then to k, well, I get the same thing. Okay, so on finite graph, this is just trivial by what I just proved. And then on infinite graph, you just take the limit when the boundary goes to infinity, okay? And you get just the same result on the infinite graph just by convergence of both measures. Okay? And then, once you're there, this is just Kolmogorov extension theorem. So this is clear by construction, but not that this measure, I cannot really describe it as I did before as just a random walk starting from somewhere, because all of my trajectories and my measure now, they are really infinite random walk, right? They run for an infinite time. And moreover, I will actually have an infinite number of such random walk, because let's say if I restrict myself to k, how many random walk do I have? I have a Poisson parameter with Poisson variable with parameter u times the capacity. And it turns out that on most graph, the capacity of k, when k goes to infinity, this goes to infinity. Okay? So what that means is that actually, as k goes to infinity, this goes to infinity, and so you have an infinite number of trajectories. Okay? Note that here, if you look at the total number of excursions, right, this is a Poisson random variable with this parameter, but let's say you're on ZD or something like that, the degree of your boundary here, this explodes, because you have all the points on the boundary of your ball which are connected to your boundary. So you have like n to the d minus 1 of them. Okay, so you have actually many walks here. This is n to the d minus 1 typically on Z. Okay, so that's why your number, when you take the limit, your number of trajectories explodes. So you have actually here, this measure it cannot be renormalized to a probability measure. It's really a measure. Magnifique measure. That's it, my friend. And so what is random interlacements? Well, this is just, as before, I take a Poisson point process with this intensity measure. Random interlacement is a Poisson point process with this intensity u times intensity. So maybe I should say random interlacement at level u, and u is your time, your parameter. And the bigger u is, the more trajectory you have, and by the more trajectory you have. By the more trajectory, I mean that restricted to a finite set, I have more trajectory. In total, I have an infinite number. And the random interlacement set, which is usually denoted by IU, this is just all the points which are visited by random interlacement. So that means that there is a trajectory in my random interlacement that visits X. So maybe if you're not too happy, let me give one word about, if you're not too happy about why do I do continuous time here, let me say, okay, you could do finite time, discrete time, if you wanted here. So just define your local time as just the number of times that your discrete chain come back in X, so you remove this exponential variable, okay? You define TU in the same way. So now the thing that changed, if you do that, is the number of excursions for my walk, okay? The number of excursions for my walk now is just constant. I just have U of them, okay? But when I, U times the degree, sorry. When I restrict it to K, what do I get? Well, each of my excursion have a probability 1 over the degree of the boundary of the capacity to each case, so I get a binomial random variable. Okay, with parameter 1 over the degree times the capacity for the first one, the second one is u times the degree. But this binomial random variable, as the degree goes to infinity, this just converges to Poisson. Okay, by the convergence of binomial to Poisson, so you would, if you were taking your limit of your graph to infinity, everything would become again Poisson, and you would get exactly the same process as here in the continuum. So that's why it's easier to just start in the continuum, because this gives you directly the correct process, even on fire graph. Okay, and one defining property of interlacement is the following, is that if I want to look at the probabilities that my interlacement hit a given set K, this is given to you by exponential minus u times the capacity. Why? Well, the only way for your interlacement set to avoid K is that there is no trajectory in K. That is that your Poisson random variable with parameter u capacity is equal to 0, which is exactly that. Okay? But not that this can be served as a definition of your interlacement if you want. I mean, then you need to prove that it exists, but there is only one random set which verifies this equality here, and it turns out that this is constructed as a point.
Can you then define trajectories out of the set?
I mean, the trajectories are nu G, this is a measure on trajectories everywhere.
No, this is not what I mean. So here, construction gives a construction for a collection of trajectories, but then IU is just a random set.
Yeah.
And as you said, you can also use this last equation as a definition of IU.
Yeah.
And this defines you a random set.
Yeah.
But can I define a collection of trajectories out of my random set?
So by what I mean by this defines your random set is that there exists only one random set such that this is true for any K finite.
But you can't recover the whole possible process of excursion.
No, I mean you cannot recover the process of excursion. I mean you can if you know what is happening, but yeah, just from this definition it's hard to see where it's coming from. I mean that's your question. So, yeah, I mean if you here were giving me something different than the capacity of K, I would not be able to tell you how to construct this set anymore, right? Yeah, I know how to do it because I've done it before and I ended up here, but otherwise it's not clear how can you do that? You take a different notion of capacity. All right. So for those of you who have heard about random interlacement, one other classical way to define them is to go through the random walk on the torus. And this is a theorem, which is another way to see random interlacement, which is windy. Which says that as n goes to infinity, the random walk on the torus, so this is a d-dimensional torus of side length n, okay, stopped at the time u n to the d, converges to random interlacement at level u. So what this means is that if you take your torus, you run a random walk on it. So converges, maybe I should say locally. I'm not going to be precise about exactly what this means. But you run your random walk in the torus, so when you end up down here, you come back on the right and so on, right? And you restrict yourself to a given set. Okay, this is a local convergence. So if you restrict yourself locally to look at what happened, then what you see is basically random interlacement. Okay. So as n goes to infinity, the size of the torus goes to infinity, and your set, let's say, is fixed. Okay, so why? It's just because this excursion of the random walk, this is just a random walk, okay? And then at some point it goes really far away, and much later it might come back, okay? But if it comes back much later, basically what was happening before coming back and after coming back are almost independent, okay? And each of these excursions, they just look like excursions from walks coming from infinity because they come from very far away. Okay, so they just look like an excursion of a walk coming from infinity because they come from very far away, and so they look like a random interlacement. That's the idea behind it. So this is another natural way, and there has been a lot of application of this to try to understand the random walk on the torus using random interlacements, because that's much easier object to study usually. So, as we have seen, the central notion that has been also discussed yesterday for random interlacement is this capacity, this notion of capacity. And I just want to give you like some idea of what is the capacity, because this will be an essential tool, and this is, I mean, this tells you, this helps you to understand how many trajectories do I have exactly in my interlacements. So I will leave the first part as an exercise. So the first equation that you can derive, and this is just a consequence of the Markov property for the walk, is that, so let me define gxy, this is the green function of your walk, and the number of times starting from x that you come back in y, and I need to renormalize because of time reversal by 1 over dx, just so that my green function is symmetric, so that gxy equals gyx. This is just a renormalization factor to make sure that I still have a symmetric object at the end. And if you sum your green function against your equilibrium measure, what you get is your heating probability of your set k. So this is true for all k and x. Okay, so this is true for y. So what this means is that, okay, let's say x is really far away from k. Then your green function is basically always of the same order, okay, because it's just the probability to go from x to y where y is far away. So it's always the same order. So you can somehow put your green function outside of your sum, and then you get a relation between your capacity and your heating probability. So the capacity, in a sense, this is something that measures how hard is it for a set to be hit by the random walk, okay? How hard is it for a set to be hit by a random walk is this probability, maybe as x goes to infinity or something like that. And this is related to the capacity via this formula. More precisely, it's related directly to the equilibrium measure via this formula, but if your green function is of constant order, you could put it out of the sum, and this will give you just the capacity up to factors. Okay? The second formula, which is a really useful formula, it's a variational principle for the capacity. And it is telling you that you can rewrite the capacity, or more precisely the inverse of the capacity, as the minimum of the sum of all the mu x, mu y, gxy over, and the infimum is over what? It's over all mu, which are probability measures, which are probability measures on k. Okay? So this is a variational principle for your capacity, and without surprise, what is the mu for which this infimum is reached? This is exactly your equilibrium measure. So you can first try to prove, okay, if I take mu, the equilibrium measure, then I get back the capacity. For that, you need to use 1, and then show that this is actually the smallest one. Okay. And so using these two properties, I can estimate the capacity of sets.
Now we are just working with the general transient graph.
Yeah. Or also finite graph with a boundary or something like that. You can also take a recurrent graph with a boundary or something like that. So corollary. So let's try to take the capacity of some simple set on ZD. And let's say, for instance, if I want to know what is the capacity of a ball. So this is a ball, you can take whatever, let's say Euclidean distance, okay, for instance, it doesn't matter. This should be of order n to the d minus 2. If you take the capacity of a line, so let's say 0n times 0 to the d minus 1. So this is of order, and this is where it becomes a bit more interesting, because this depends on the dimension. So in dimension 3, this is of order n over log n. And in higher dimension, this is of order n.
So now you are on ZD.
Yes, I'm on ZD. Another set that will be important later is to look at a rectangle, or a tube, if you want. So I take, instead of taking 0n times 0, I take 0n times 0L, where L is smaller than n. And what this is that this is C, I mean, up to constant anyway, n over log maximum of 2 n over L, if d equals 3. So again, there's this dichotomy between d equals 3 and d larger than 4. And in larger dimension, this is just n. And you can check that if I take L equals 0, I come back to here, and if I take L equals n, I come back to here. So this interpolates between the two previous results. Okay. And the last result I want to mention is the capacity of a random walk. The random walk, this will be something, and if you take, let's say, the random walk inside a ball, this will be something that will be between the capacity of a line, because you hit over the r squared point, not r, right? And the capacity of a ball. So this will be something in high dimension, for instance, it will be between n and n to the d minus 2. And it turns out that, so here I will write it for this, but you could take other things, but maybe it's a bit easier to prove for that, so I'll write it like that. So let's say I look at the average value of the inverse of the capacity. This is of order, and there you will have 3 cases. In dimension 3, this is 1 over square root of n. In dimension 4, now 4 is the critical dimension, if d equals 4. And in a higher dimension, this is 1 over n. So this is all inverse because I put a minus 1 compared to the previous one. Yeah. And this is a Rav. So I will leave the proof as an exercise. Maybe let me tell you how do you deduce the corollary from these formulas here. Well, for the first one, this is just a direct consequence of this because your green function is always of order the distance to the power d minus 2. If you take x equals 0, okay, then this is a direct consequence of just formula 1, easy one. The formula 2, for the lower bound, you need to use this formula, but you just take mu x to be constant. Okay, so it's a 1 over the cardinality of k. And this just then tells you, okay, you just need to sum the green function. And it turns out that if you sum the green function, you will get exactly the above result. So the green function is about the distance to the d minus 2, right? Minus d minus 2. And for the last one, this one is a bit more complicated, okay, for the capacity of the random walk. But basically, if you just want, let's say, the lower bound, what you need to do is you need to use this formula. But you need to take mu x to be the local time, or to be proportional to the local time at x. So how many times did I come back in x, divided by n, okay, so just so that this is really a probability measure. If you take mu x to be the local term of x, basically you will have a sum over all times of the green function, and this you can estimate, and this will give you this result here. Okay, so this is how you prove this final result, and I will stop here for today.
So maybe we have time for one quick question.
So for C, this constants depend on L, right?
No.
No.
No. I mean, oh, because I forgot something. Thank you. This is important, indeed. So that it indeed interpolates between the two.
It's not just an expectation, it's also defined probability in terms of.
Yeah, I will come back to that next tomorrow. But indeed.
So let's thank Alexis again.